A relentless cosmic clock has been ticking since the very first moment. Its gears were forged in the fiery birth of the universe, and its hands sweep across billions of years, pushing everything forward. This is the engine room of reality, and its fundamental fuel is a force you encounter every day: entropy. By the end of this journey, you will see the entire story of the cosmos, from the Big Bang to the distant future, as a single, unified narrative. We will uncover why time only flows in one direction, and how the same law that governs a cooling cup of coffee also dictates the fate of stars. What does the idea of a one-way universe make you wonder about most? That cooling cup of coffee on your counter holds a secret law of the cosmos. We see it happen all the time. The steam rises, the warmth fades, and eventually the coffee reaches the same temperature as the room. It never goes the other way. A lukewarm cup never just decides to heat itself up again. This simple, one-way street is a perfect picture of the second law of thermodynamics. At its heart, this law is about a quantity called entropy, which is a measure of disorder or randomness in a system. The law says that in any isolated system, the total entropy always increases. The heat from your coffee doesn't vanish. It spreads out, moving from the concentrated, organized state in the cup to a disorganized, chaotic state across countless air molecules in the room. This journey from order to disorder is a one-way trip, and it applies to everything, not just your morning brew. Think of a drop of ink in a glass of water. It starts as a neat, dark blob, a state of high order, but it never stays that way. The ink particles spread out, mixing randomly with the water until the entire glass is a uniform, faint color. That is entropy increasing. The organized ink droplet has dissipated into a disordered, mixed state. This is the universe's default setting. Energy and matter tend to spread out, to even out, to move from concentrated and useful to diffuse and random. This is the silent, relentless force that was set in motion at the very beginning of time. So the next time you see ice melt in a drink or smell perfume diffuse through a room, you are watching a tiny echo of the same process that guides the life and death of stars. But this idea of disorder can be misleading. It is not about a messy room versus a tidy one. The true engine is probability. Think of a brand new deck of cards fresh from the box. The cards are in perfect order, ace through king, all the suits lined up. There is only one way for the deck to be in that exact, pristine sequence. Now shuffle the deck just once. The cards become randomized. There are not just a few possible arrangements anymore. There are more ways to arrange a standard deck of cards than there are atoms on Earth. An unimaginable number of possibilities. The universe is like that master shuffler. It is constantly mixing things up, and it is far more likely to land on one of the countless disordered states than on the single, perfectly ordered one. Entropy is simply a measure of this probability. A state of high entropy is not necessarily more chaotic. It is just statistically inevitable. There are simply more ways for things to be mixed up than for them to be perfectly arranged. This is why a shattered vase will not spontaneously reassemble. It is not impossible, just so incredibly unlikely that you could wait for the entire lifetime of the universe and never see it happen. The molecules would have to randomly find their way back to the exact right positions against astronomical odds. This probabilistic view transforms entropy from a vague idea about mess into a precise mathematical force. It explains why time has a clear arrow. The past is a state of lower probability, a more ordered arrangement. The future is a state of higher probability, a more scattered one. And the universe always rolls the dice in favor of the most likely outcome. So every time you see ink mix into water or heat flow from hot to cold, you are not just watching energy disperse. You are witnessing the universe playing the odds, moving relentlessly from the improbable to the probable, from the rare to the common. This statistical foundation is what gives entropy its immense power, a power that dictates the fate of everything, from a single atom to the largest galaxy. This statistical inevitability is the very reason you remember your first day of school, but not what you will have for lunch next Tuesday. The flow of time itself, that relentless forward march we all experience, is tied directly to the rising tide of entropy. Why does time have a clear arrow pointing only from past to future? The universe does not have a giant clock dictating this direction. Instead, the arrow of time emerges from the overwhelming probability that disorder will increase. The past is by definition a state of lower entropy. It is a more ordered, less probable arrangement of the universe's components. The future is a state of higher entropy, a more scattered and statistically likely state. Our own consciousness is swept along by this current. Think about how a memory is formed. It is not a magical imprint. When you experience an event like blowing out birthday candles, a cascade of electrical and chemical activity fires through your brain. This process disperses energy, increasing the entropy within your neural circuits. That specific, complex pattern of activity is the memory being written. To remember the future, your brain would have to somehow gather that dispersed energy back into a highly ordered state, effectively reversing the increase in entropy. That would be like the smoke and heat from the candles rushing back to reform the unburned wax and the lit match. It is not forbidden by the laws of physics in a strict sense, but it is so astronomically improbable that it is effectively impossible. This is why cause always precedes effect. A cause is a more ordered state that releases energy, creating a less ordered effect. A falling domino hits the next one because the potential energy stored in its upright position is released into motion and sound, increasing the disorder of the system. You could never see the effect happen first. You will never see a domino spontaneously stand up because the sound waves in the room and the heat from friction all conspired to push it upright. That sequence would require a massive, localized decrease in entropy, a reversal of probability on a cosmic scale. So the reason you have a past and are moving into a future is not a philosophical mystery. It is a physical one. You are a witness to and a product of the universe's journey from a state of low probability to a state of high probability. Your very ability to experience a sequence of events, to feel time passing, is a direct consequence of entropy's relentless climb. That initial low entropy state was the universe's most precious and improbable resource. To grasp the sheer strangeness of the Big Bang, we must abandon the image of a colossal explosion. It was not an eruption of matter into a pre-existing empty space. Instead, it was the sudden, rapid expansion of space itself and everything in it from a point of infinite density. In that first fleeting moment, the entire cosmos was compressed into an unfathomably hot, dense, and radically simple state. And here is the crucial paradox. We might think of such extreme conditions as the ultimate chaos, but for entropy, it was the opposite. This was a state of profound order. The universe was almost perfectly smooth, a uniform soup of energy where differences in temperature and density were negligible. There were no clumps of matter, no stars, no galaxies, no structures of any kind. Just a blazing, featureless sea of fundamental particles. This uniformity is the hallmark of low entropy. Think back to the deck of cards. A perfectly ordered deck has low entropy. The Big Bang was the cosmic equivalent of that pristine deck, a state with very few possible arrangements. This was the spring wound impossibly tight. Since that first moment, the universe has been doing one thing: unwinding. As space expanded and cooled, that perfect uniformity began to break. Tiny, random quantum fluctuations were stretched across the cosmos, becoming the seeds for all future structure. Gravity began to pull matter together into the first stars and galaxies. This clumping, this creation of complex order from simple beginnings, might seem like a decrease in entropy, but it is not. The formation of a star is a local act of organization paid for by a massive, cosmic increase in disorder. The intense gravitational collapse releases a staggering amount of energy, primarily as light and heat, which floods out into the cold emptiness of space, spreading out and increasing the overall entropy of the universe far more than the local order of the star decreases it. So the very evolution that builds galaxies and planets is fueled by the dispersal of energy from that initial low entropy state. Why did the universe begin in such a special, finely tuned condition? This remains perhaps the deepest question in all of science. Was it a random accident, a necessary boundary condition, or a clue to a reality far larger than our own? Whatever the answer, that singular starting point set the ultimate direction for everything, giving time its arrow and the cosmos its story. A star's brilliant light is the signature of entropy's great work. That vast, diffuse cloud of hydrogen gas drifting in the void is already in a state of relative disorder, but it holds a potential for something far more dramatic. Under the relentless pull of its own gravity, this cloud begins to collapse. It shrinks, heats up, and spins faster, transforming from a shapeless haze into a dense, fiery sphere. This seems like a triumph of order over chaos, a structure being born from randomness. Yet this local act of creation comes with a cosmic price tag. The true magic and the true source of entropy's increase ignites deep within the core. Under unimaginable pressure and temperature, hydrogen atoms are forced together, fusing into helium. This nuclear fusion is a furnace of unbelievable power, but that energy must go somewhere. It floods outward from the core as intense radiation, a torrent of light and heat that pushes against the crushing weight of the star's outer layers, creating a stable balance for millions or billions of years. Crucially, this radiant energy does not stay contained. It escapes the star's surface and streams out into the frigid, near-perfect vacuum of interstellar space. This is the ultimate dispersal. The highly concentrated, organized energy within the star is scattered across light years, warming dust grains and empty space with its diluted warmth. The local order of the star, its complex internal structure and sustained fusion reaction, is made possible only by this massive export of disorder into the wider universe. The star's brilliant light is the very means by which it increases the cosmos's total entropy. It is a temporary island of intense organization, shining only because it is furiously casting its disorder out into the cold, dark sea around it. Yet even the brilliant furnace of a star is a fleeting event in entropy's grand scheme. The true champions of disorder emerge from the most catastrophic stellar deaths. When a massive star exhausts its nuclear fuel, the balance shatters. Gravity, no longer held at bay, crushes the star's core with unimaginable force. For the most colossal stars, this collapse does not stop at forming a dense neutron star. It continues, compressing matter into a point of infinite density, a singularity, and warping spacetime so severely that not even light can escape. This is a black hole, and within its dark heart lies the ultimate expression of entropy, A black hole is not a void of nothingness. It is a cosmic vault, and its entropy is staggeringly vast. The work of physicists like Jacob Bekenstein and Stephen Hawking revealed a profound truth. The entropy of a black hole is not hidden in its mysterious interior. It is written on its boundary, the event horizon. The surface area of this point of no return is the measure of its disorder. The larger the black hole, the greater its entropy. In fact, a black hole contains the maximum possible entropy that any region of space of that size can hold. Think of the event horizon not as a simple wall, but as a surface composed of unimaginably tiny pixels, each one encoding a fundamental bit of information. A stellar mass black hole possesses more entropy than all the stars, planets, and cosmic dust in the entire galaxy combined. This turns our intuition on its head. To our eyes, a black hole appears as the most ordered, simplest object imaginable, defined only by its mass, spin, and charge. But this simplicity is an illusion, a mask for an interior state of such profound disorder that it dwarfs all other cosmic structures. They are the universe's ultimate entropy sinks, the final resting places where information and disorder are compressed to their absolute limits. Their existence forces us to confront the deepest links between gravity, quantum mechanics, and the relentless flow of time. As black holes grow, merging and consuming gas, they do not erase entropy. They concentrate it, accounting for a significant portion of the cosmos's total disorder budget, and pushing our understanding of reality itself to the brink. But how does a living, breathing being fit into this cosmic slide toward disorder? A cell, a tree, a human brain all represent islands of breathtaking order. They build intricate structures, process information, and maintain a precise internal environment against all odds. This appears to be a direct rebellion against the second law, a local reversal of entropy's tide. The truth, however, is far more ingenious. Life does not break the universal rule. It has become a master of exploiting it. Every living organism is an open system, constantly trading with its environment. To maintain its delicate internal order, it must import order from elsewhere. You do this every day. You consume food, a highly organized, energy-rich source of low entropy. Your body breaks down these complex molecules, extracting the useful energy to power your cells, build new tissues, and maintain your body temperature. In return, you release waste products and heat into your surroundings. That exhaled breath, that radiated warmth, represents a massive export of disorder. The increase in entropy from the waste you produce far outweighs the local decrease in entropy that is your continued existence. You are a temporary eddy in a flowing river, a whirlpool that seems to have its own structure and direction. But that whirlpool can only persist because of the relentless flow of water passing through it. For life on Earth, that flow is the radiant energy from our sun. Sunlight is a stream of low-entropy energy, a focused and useful form of power. Plants capture this energy, using it to build sugars from carbon dioxide and water, effectively packaging order into chemical bonds. Animals then consume the plants or other animals, and the process continues. Life is a complex chain of entropy transactions, a brilliant and temporary rebellion made possible only by speeding up the overall dispersal of energy into the cold darkness of space. We are not exceptions to the cosmic rule. We are its most sophisticated and beautiful expression. The order we see in a living cell or a swirling galaxy is built from information. This information is not a ghostly, abstract concept. It has weight and consequence, a physical reality that ties it directly to the engine of entropy. In the middle of the 20th century, a researcher named Claude Shannon was trying to solve a very practical problem: how to send messages clearly over a noisy telephone line. In his work, he stumbled upon a revolutionary idea. He needed a way to measure information, and he called this measure information entropy. The mathematics he developed looked almost identical to the equations physicists used for thermodynamic entropy. This was no mere coincidence, it was a profound clue. Shannon had discovered that information is a form of order, and its absence, uncertainty, is a form of disorder. The more unpredictable a message is, the more information it contains. A perfectly predictable message, like a string of identical letters, carries no real information at all. This deep link means that every bit of information, every 1 or 0 in a computer, has a physical footprint. Think of a single bit in a computer's memory. It might be represented by a tiny transistor that can be in one of 2 states, charged or uncharged, representing a 1 or a 0. Now, imagine you want to erase that bit, to reset it to a 0 regardless of its previous state. To do this, the computer must physically manipulate that transistor, forcing it into a definite state. This act of erasure, of wiping out a piece of information, is not free. The physicist Rolf Landauer showed that it necessarily produces a tiny amount of heat. When you erase the information about what the bit was before, you are effectively increasing the disorder of the surrounding environment. You are making the universe forget, and that act of forgetting releases energy as heat, increasing the total entropy. This is Landauer's principle, a fundamental limit on computation. It means that forgetting, the loss of information, is an irreversible process that pays an entropy tax. Every time you clear your browser history or delete a file, your computer isn't just freeing up space. It is generating a minuscule amount of heat, contributing its own tiny whisper to the universe's growing hum of disorder. The cosmos, therefore, is not just a machine running on energy. It is a computer processing information, and every calculation, every memory formed and forgotten, is another turn of the great cosmic wheel, pushing reality forward along its one-way street. This vast computation, this cosmic exchange of information for heat, cannot run forever. The universe's ultimate destination is a state of perfect, silent equilibrium, a final stillness known as the heat death. Picture the cosmos not with a bang, but with a whisper, a slow and irreversible fading of all its lights. Every star, from the mightiest blue giant to the faintest red dwarf, will eventually consume its nuclear fuel. Their fires will gutter out one by one, leaving behind cold, dark remnants like white dwarfs and neutron stars, slowly radiating their last residual heat into the abyss. Even the universe's ultimate vaults of disorder, the black holes, are not permanent. Through the subtle quantum process of Hawking radiation, they too will gradually leak their mass and energy back into space, evaporating over timescales so vast they defy comprehension. What remains is a cosmos transformed into a featureless, lukewarm sea. All the energy that once powered galaxies and life itself will have spread out uniformly. There will be no hot spots and no cold spots, no regions of high or low concentration. Every corner of the universe will be at the same, incredibly low temperature. In this state of maximum entropy, the cosmic engine finally grinds to a halt. With no energy gradients, no differences in temperature or pressure, no work can be done. It is like a battery that is completely drained or a clock whose spring has fully unwound. There can be no motion, no structure, no further change of any kind. Time, as we understand it, may lose all meaning, for without a sequence of events, without cause and effect, the arrow of time itself might cease to point. The universe would be frozen in a single, eternal moment, a permanent and uniform sameness stretching across an infinite, dark expanse. This is the logical, inescapable conclusion of the second law's reign, the final, quiet victory of probability. Yet this grand narrative of a universe sliding into equilibrium is not the final word. The engine room of reality still holds profound mysteries that challenge the simplicity of this picture. For instance, why did the universe begin in that special low entropy state at all? The second law tells us what happens next, but it does not explain the initial winding of the spring. Some physicists propose our Big Bang was not a true beginning, but one phase in an endless cycle. In these models, like the conformal cyclic cosmology, a universe in its final heat death might, through a complex transformation, become the high-energy, low-entropy seed for a new Big Bang. Others look to the multiverse, a vast landscape of countless universes, each with different physical laws. In such a cosmos, we simply find ourselves in one of the rare universes where the initial conditions were just right for stars, planets, and life to emerge. These ideas are speculative, but they highlight that the low-entropy beginning might be the real puzzle, not the subsequent climb toward disorder. Adding to this mystery is the enigma of dark energy. This mysterious force is causing the expansion of the universe to accelerate, pushing galaxies apart at an ever-increasing rate. For the long-term forecast of entropy, this is a game-changer. An accelerating expansion does not lead to a quiet, static heat death. Instead, it can create a far more dramatic and isolating end, often called the Big Freeze. As space stretches faster and faster, distant galaxies will vanish over the cosmic horizon, leaving our observable universe an island of dwindling resources. Eventually, even the fabric of space itself may grow so cold that it tears apart the very atoms that remain. This accelerated expansion could also influence how black holes evaporate and how information is ultimately processed, suggesting that our current understanding of the final state is still incomplete. These open questions are not failures of the theory, but signs of a science that is alive and evolving. The story of entropy is not a closed book. It is a living narrative with each new discovery, from the quantum nature of black holes to the properties of dark energy, adding a new paragraph or rewriting an old chapter. The engine room is more complex than we first imagined, and its deepest secrets are still waiting to be uncovered. This quantum dance of probability is not confined to isolated particles. It spills over into the relationships between them, creating connections so strange they seem to defy the very nature of space and time. This is the phenomenon of quantum entanglement, and it presents a profound puzzle for our understanding of information and disorder. When two particles become entangled, their fates are linked in an intimate, instantaneous way. Measuring the property of one particle, like its spin, will instantly determine the property of the other, no matter how far apart they have traveled. This creates a correlation that is stronger than any classical link. It is as if you had a pair of magic coins. You flip one coin in New York and see it land on heads. At that exact moment, you know with absolute certainty that the other coin, spinning in Tokyo, has landed on tails. This deep connection seems to create a kind of order, a hidden structure woven into the fabric of reality. Yet this order does not come for free. The act of measuring an entangled pair, of forcing this potential into a definite reality, has consequences. It disrupts the delicate quantum state, and this disruption increases entropy. The information about the particles' shared past is, in a sense, lost or scrambled when we look at them. Physicists are now developing new measures of entropy to capture these unique quantum correlations, realizing that the classical idea of disorder is too simplistic for this spooky realm. Understanding quantum entropy is more than an academic exercise. It is a critical step toward the holy grail of modern physics, a complete theory of quantum gravity. The universe's largest structures, like black holes, are governed by gravity, but their ultimate fate is dictated by quantum mechanics. To truly understand the engine room of reality, we must speak both languages fluently. We need to know how the probabilistic whispers of the quantum world amplify into the thermodynamic roar that shapes our cosmic destiny. The bridge between these two domains is being built with the tools of quantum information, suggesting that at the most fundamental level, the universe is not just about energy and matter, but about the relationships between them. The keys to unlocking the final secrets of entropy, time, and existence itself are waiting to be found in this strange, probabilistic underworld. Gravity stands apart in this cosmic drama, a force with a dual nature that is both creative and destructive. While the other fundamental forces tend to smooth things out, to disperse energy, gravity does the opposite. It is a relentless pull toward concentration. In the early universe, it was gravity that took the faint ripples in the cosmic fabric and amplified them, gathering scattered clouds of hydrogen into the first brilliant stars. It sculpted spiral galaxies and assembled planets, creating the very stages upon which life could emerge. This seems like a direct contradiction to the second law. How can a force that builds such magnificent order be a servant of disorder? The answer lies in what happens when matter is forced together. A star is not just a pretty light in the sky. It is a cosmic pressure cooker, and gravity provides the crushing pressure. By pulling an immense amount of gas into a tight sphere, gravity creates the extreme temperatures and densities necessary for nuclear fusion to ignite. This is the key. The fusion reactor at a star's core is an incredibly efficient machine for generating entropy. It takes a concentrated fuel, hydrogen, and transforms it into a less useful waste product, helium, while releasing a flood of high-energy photons. This light then begins a long journey. It bounces around inside the star for thousands of years, slowly losing energy, before finally escaping into the cold vacuum of space. That escape is the ultimate act of dispersal. The star's brilliance is the visible signature of energy spreading out, of the universe's disorder increasing. So gravity's act of creation is actually a clever trap. It builds a concentrated source of fuel precisely so that it can be burned, releasing a far greater amount of disorder than if the gas had just drifted apart slowly. The more massive the object gravity creates, the more profound its entropy-producing power becomes. A black hole represents the ultimate triumph of this process. By crushing matter into a singularity, gravity creates an object whose entropy, encoded on its event horizon, is greater than that of an entire galaxy of stars. Gravity, the great organizer, is ultimately the universe's most prolific disorganizer. It designs the most spectacular fireworks only to ensure their light spreads as far and wide as possible. This initial smoothness, the universe's pristine low-entropy state, was not a lucky accident. It was the result of a violent and transformative event that occurred in the first fleeting moments of existence, a process known as cosmic inflation. To understand this, we need to rewind the clock even further, to a time so close to the Big Bang that our current laws of physics begin to falter. In this unimaginably dense and energetic realm, a peculiar type of energy, a repulsive gravity, is thought to have taken hold. This energy did not pull things together. It pushed space itself apart, and it did so at a rate that defies all intuition. For a sliver of a second, the universe did not just expand. It underwent exponential expansion, doubling in size repeatedly, faster than the speed of light. In that incomprehensibly brief burst, a region of space smaller than a single subatomic particle was stretched to a size larger than our entire observable universe today. This violent smoothing process is the key. Before inflation, the infant universe may have been a chaotic, crumpled mess, full of wild variations in energy and density. But inflation acted like an cosmic iron. By stretching space so tremendously, it smoothed out those wrinkles. Any large-scale irregularities were stretched so thin that they became negligible across the vast new volume. What was left was an incredibly uniform, flat, and smooth cosmos, the perfect low-entropy starting point we observe in the cosmic microwave background. Think of it like stretching a piece of knotted, wrinkled rubber sheeting. As you pull it taut in all directions, the knots and wrinkles are smoothed away, leaving behind a vast, flat surface. Inflation did exactly this to the fabric of spacetime. It took a potentially messy, high-entropy beginning and transformed it into the organized, low-entropy slate necessary for everything that followed. This theory provides the missing piece of the puzzle, the catalyst that primed the cosmic engine. Without that explosive smoothing, the universe might have remained a tangled, high-entropy knot, unable to form the structures that lead to stars, planets, and us. Inflation set the stage, creating the initial order that entropy would then spend the next 14 billion years diligently unraveling. Our ability to witness the cosmic drama is not a detached observation. It is a necessary consequence of the stage upon which we find ourselves. The very fact that you are here, conscious and curious, asking questions about the nature of time, is deeply intertwined with the law of increasing entropy. For life and the complex structures that support it is an emergent property of a universe that is far from equilibrium. Think of a universe that had already reached its final state, the heat death. It would be a vast, lukewarm, and utterly uniform bath of energy. There would be no planets, no stars, no differences in temperature or pressure. In such a perfectly balanced cosmos, no work can be done. There can be no whirlpools, no storms, no intricate chemical reactions. Most importantly, there can be no brains to process information, no senses to perceive the world, no consciousness to wonder about its own existence. We could not be there to see it. Now consider a universe without a clear arrow of time, one that oscillated or had no strong preference for moving from order to disorder. In such a chaotic environment, stable, long-lasting structures would be impossible. A planet might form one moment only to dissolve into its constituent atoms the next. The consistent cycles of day and night, the predictable orbits of celestial bodies, the very reliability of cause and effect that allows life to evolve and intelligence to develop, would all be absent. Our existence, therefore, is not just compatible with a universe of rising entropy. It demands it. The long, slow climb from the low-entropy Big Bang is the only possible timeline that could have produced us. We are not accidental tourists in this cosmos. We are the products of its fundamental operating principle. This idea is known as the Anthropic Principle. In its simplest form, it suggests that the universe we observe must be compatible with the existence of observers. It does not explain why the universe has the particular laws it does, but it does tell us why we shouldn't be surprised to find ourselves in a universe capable of generating galaxies, stars, planets, and life. We are children of the cosmic gradient, born from the immense power difference between a hot, dense beginning and a cold, empty end. Our consciousness is a flicker of awareness in the vast, darkening theater of existence, a temporary echo of the universe's initial, improbable state. This speculation leads us to the most intimate frontier of all, the human mind itself. Could the relentless climb of entropy be the very source of our conscious experience, the reason we feel time flowing from past to future? Some thinkers propose that the brain is not just a passive observer of the universe's one-way street, but an active participant whose very operation generates our sense of time. Your stream of consciousness, that continuous narrative of thoughts and sensations, might be a direct reflection of the brain's constant, irreversible processing of information. Every memory you form, every decision you make, involves electrical signals firing and chemical messengers crossing synapses. These are physical processes, and like all physical processes, they increase entropy. When a neuron fires, it doesn't just send a signal, it dissipates energy as heat and creates a more disordered state in its wake. The act of remembering your first kiss, for instance, is not a perfect replay. It is a reconstruction, a new neural event that consumes energy and increases local disorder within your brain. This continuous, irreversible cascade of neural activity, always moving from a state of potential to a state of actualized, dispersed energy, may be the physical substrate of your subjective timeline. The past feels fixed because the neural patterns that encode it have been laid down, their entropy already increased. The future feels open because your brain has not yet performed the thermodynamic work of choosing, acting, and remembering. In this view, your conscious self is not a ghost in the machine, but the feeling of the machine itself running, of information being processed and entropy being paid as the price for each moment of awareness. While this idea remains a profound hypothesis, it hints at a breathtaking unity. The same fundamental force that guides the evolution of galaxies might also be whispering in the corridors of your mind, shaping not just the cosmos you inhabit, but the very experience of being you within it. Our cities glow brightly against the night sky, visible even from orbit, and that light is a testament to our planetary scale manipulation of entropy. Every power plant, from a massive hydroelectric dam to a simple solar panel, is a device for managing the flow of energy from a concentrated source to a dispersed state. We burn fossil fuels, releasing energy stored by ancient sunlight over millions of years in a geological instant. We split atoms, unleashing the immense binding energy hidden within matter itself. All of this concentrated power is channeled to build and maintain our complex societies. We construct towering skyscrapers from raw iron ore, assemble intricate computer chips from common sand, and weave global communication networks that process unimaginable amounts of information. Each of these achievements represents a local pocket of profound order, a seemingly defiant act of organization. Yet this order is purchased with a steep cosmic debt. For every watt of electricity that powers a city, for every joule of energy that propels a vehicle, waste heat is generated and dissipated into the atmosphere. Our industrial processes produce not only the goods we use but also pollution, a tangible signature of disorder spreading through our air, water, and soil. We are, in effect, taking the planet's stored energy gradients and rapidly flattening them, accelerating the journey toward a more probable, more disordered state on a global scale. This makes human civilization one of the most potent entropy-producing forces this planet has ever seen. We are not separate from the universe's thermodynamic story. We are a dramatic, fast-forward chapter within it, demonstrating a profound truth. The creation of complex technological order is not a violation of the second law, but its most sophisticated expression. Our intelligence allows us to become conscious agents of entropy, directing its flow to build temporary wonders while inevitably contributing to the larger, relentless dispersal of energy. This cosmic perspective on energy and decay is not merely a scientific observation. It carries a profound ethical weight, a responsibility that falls squarely upon our shoulders. We are the temporary custodians of a precious and finite inheritance, the concentrated energy that our planet has accumulated over billions of years. The second law of thermodynamics is not a suggestion. It is an unforgiving accounting of the universe's energy budget, and every action we take is a withdrawal from that dwindling account. The concept of sustainability, then, transforms from a political slogan into a fundamental cosmic principle. It is the conscious decision to align our local activities with the long-term flow of the universe, to manage our entropy production with wisdom and foresight. Efficiency is not just about saving money. It is a moral act, a way of maximizing the meaningful work and beauty we can create from each unit of energy before it is inevitably lost as waste heat. When we design a more efficient engine or build a better insulated home, we are not just optimizing a system. We are stretching out the timeline of possibility, prolonging the conditions that allow for art, science, and civilization itself. Our environmental crises, from climate change to resource depletion, can be seen through this lens. They are not simply problems of pollution. They are symptoms of a profound thermodynamic imbalance, where our rate of consuming low-entropy resources vastly outpaces the planet's ability to regenerate them. We are spending our cosmic capital as if it were interest, accelerating our local journey toward a high-entropy state. This frames our choices in a starker, grander light. The decisions we make today about energy, consumption, and technology are not isolated events. They are echoes that will resonate for generations, determining how long this vibrant pocket of order we call human civilization can persist against the relentless tide. We are, for a brief moment, the universe become conscious of itself, and with that awareness comes the duty to steward its energy wisely. The paint on a canvas cracks and fades just as a star exhausts its fuel. This inevitable decay is not just a subject for art, it is the very medium of its existence. Artists have long been unofficial physicists, intuitively mapping the universe's deepest laws onto canvas, stone, and sound. The Romantic painters did not need equations to understand entropy. They felt it in the melancholy beauty of a ruined castle being reclaimed by ivy and weather. They were depicting a local rebellion against time, a structure of order slowly surrendering to the overwhelming probability of disorder. The grandeur of those paintings comes from the tension between the human desire for permanence and nature's relentless pull toward dissolution. This theme echoes through centuries, from the memento mori of still life paintings, with their wilting flowers and rotting fruit, to the weathered sculptures of ancient civilizations. Each piece is a meditation on the second law, a silent acknowledgement that all things move from a state of low probability to high probability. Then came the modern era, and the exploration of entropy became even more direct. The chaotic drips and splatters of Jackson Pollock are not random. They are a controlled release of energy, a deliberate orchestration of chaos that captures the moment of creation and dissipation simultaneously. The artist becomes a force of nature, guiding paint in a way that mirrors the universe's own tendency to mix and scatter. In music, the same principle applies. A symphony begins with a simple, ordered theme, a low-entropy state. As the piece progresses, the theme is developed, varied, and fragmented. It reaches a climax of complexity and energy, a high-entropy state of sound, before finally resolving back to a quiet, simpler chord. The journey of the music is a thermodynamic process in sound, a story of building and releasing tension that resonates with our own experience of time's arrow. Even our digital world, with its pristine streams of ones and zeros, is subject to this aesthetic. Glitch art intentionally introduces errors and corruption into digital files, creating beauty from the breakdown of perfect order. These artifacts are a reminder that even in the most controlled systems, disorder will find a way to express itself. art, in all its forms, is humanity's way of externalizing our relationship with the cosmos's fundamental narrative. We do not just observe the flow from order to disorder, we participate in it, we mourn it, and we find a strange, profound beauty in its inevitability. But this grand cosmic slide toward equilibrium is not quite as absolute as it seems. The same statistical rules that demand disorder also permit a strange and unsettling loophole. In a universe that has truly reached heat death, a state of maximum entropy and perfect uniformity, change has not been outlawed. It has merely become incredibly, almost infinitely, unlikely. The probabilistic dance of particles never completely stops. Given enough time, an almost endless amount of time, random chance will eventually conspire to create a brief deviation from the silence. A few atoms might randomly jostle together to form a fleeting, simple structure. Given even more time, a fluctuation could, by pure accident, assemble something far more complex. In theory, a random fluctuation in the void could spontaneously form a fully functioning, self-aware human brain, complete with a lifetime of false memories, convinced it exists in a real world. Physicists call this spectral possibility a Boltzmann brain. The paradox this creates is staggering. If the universe is destined for an eternal, high-entropy equilibrium, then the number of Boltzmann brains appearing randomly in the void should, over infinite time, vastly outnumber the ordinary brains that evolved in a low-entropy universe like ours. So, statistically speaking, you are far more likely to be a momentary flicker of consciousness in an endless dark, a ghost with imaginary memories, than a real person living in a real cosmos with a real history. Yet here we are, observing a universe that is clearly young and structured, with a coherent past stretching back billions of years to a low-entropy beginning. This contradiction forces a critical re-evaluation of our assumptions. Perhaps the universe is not infinite and eternal in the way the classical heat-death scenario suggests. Perhaps something prevents it from ever reaching that final equilibrium. Or perhaps our Big Bang was a truly singular event that reset the cosmic clock. The Boltzmann brain is not a prediction. It is a reductio ad absurdum, a logical argument that highlights the profound strangeness of our actual situation. It screams that our low-entropy beginning is not a minor detail. It is the central feature of reality, the one piece of the puzzle we still do not fully understand. Your own memories are a fragile bulwark against an ocean of forgetting. The neural pathways that hold a childhood birthday party, the scent of rain on hot asphalt, the precise sound of a loved one's voice, these are not permanent etchings. They are dynamic patterns constantly being reinforced or allowed to fade. Each time you recall a memory, you are not playing back a perfect recording. You are reconstructing it, and in that process, some details are subtly altered, some are lost forever. This is the second law of thermodynamics operating within the architecture of your mind. To form a memory, your brain consumes energy, creating a specific, ordered pattern of neural connections, but maintaining that order requires constant work. Without reinforcement, the pattern degrades, synapses weaken, connections fray, and the sharp image becomes a blur. This forgetting is not a failure of the brain. It is a necessary act of thermodynamic housekeeping, a local increase in entropy that allows for new learning and adaptation. If every memory were perfectly preserved, your mind would become a rigid, overcrowded library, unable to form new connections. Forgetting is the price we pay for a flexible and efficient consciousness, a direct echo of the universe's preference for scattering information over hoarding it. This principle scales up from the individual to the collective. An ancient clay tablet, baked hard in a long-forgotten fire, survives for millennia, while the vast majority of papyrus scrolls and wooden tablets from the same era have crumbled to dust. The information on that tablet persists not because it is important, but because its physical medium happened to be more resistant to the ravages of time, to the entropic forces of weather, bacteria, and decay. Every historical archive, every digital server, is engaged in a constant battle against this inevitable dispersal. Documents yellow and become brittle. Magnetic fields on hard drives weaken over time, leading to bit rot where ones slowly flip to zeros. Civilizations themselves rise, creating immense structures and complex societies, only to eventually fall. Their cities are reclaimed by forests, their languages forgotten, their knowledge scattered. This is not a metaphor. The fall of an empire is a massive, societal-scale increase in entropy. The concentrated order of a centralized state dissolves into the disorder of scattered tribes, lost technologies, and buried ruins. The very arrow of history, the fact that we have a detailed record of the past but only speculation about the future, is written by entropy. The past is a state of lower entropy, a more ordered arrangement of events whose traces, however faded, persist into the present. The future is a state of higher entropy, a realm of countless possibilities that have not yet been collapsed into a single recorded timeline. Entropy is the author of history, ensuring that the footsteps of time point in only one direction, from the ordered specificity of what was to the disordered potential of what might be. So if the second law is the engine's unstoppable rhythm, what is the source of its power? Could this fundamental rule of increasing disorder actually be a consequence of something even more basic? This question drives physicists to the very edge of known science. The second law might not be a primary law of nature at all, but rather an emergent phenomenon, a large-scale pattern that arises from the collective dance of trillions upon trillions of particles. Think of a bustling city seen from high above. The traffic flows in predictable patterns with rush hours and quiet nights. These patterns are not written into the laws of physics governing each car. They emerge from the countless individual decisions of the drivers. In a similar way, the relentless increase of entropy could be the macroscopic signature of microscopic chaos, a statistical trend so overwhelming it appears as an ironclad law. The true blueprints for reality may lie deeper in the quantum realm, at the most fundamental level where particles are fuzzy probabilities and space-time itself may be woven from discrete grains. The arrow of time might find its origin. Some theories suggest that the very expansion of the universe, stretching the fabric of space-time, creates a natural direction for quantum processes to unfold. Others probe the nature of gravity, the one force that seems to orchestrate disorder so effectively. The quest is to find a single, unified framework, a theory of everything that can seamlessly blend quantum mechanics with general relativity. In such a theory, the second law would not be an assumption but a prediction, a necessary outcome of the universe's most basic operating system. The engine room's blueprints are still hidden, written in a language we are only beginning to decipher. That very sense of being an author in your own story, of making choices that ripple into the future, feels like the ultimate defiance of a predetermined cosmos. If the universe is just a complex clockwork unwinding along a fixed path, where does our own will fit in? This ancient philosophical puzzle finds a new dimension when viewed through the lens of entropy. Our brains are not passive observers of the universe's slide toward disorder. They are incredibly active, dynamic systems, constantly processing information and making predictions. Every decision you make, from choosing what to eat for lunch to pursuing a lifelong goal, involves a physical process within your neural circuitry. electrical signals fire, neurotransmitters are released, and energy is consumed. This activity increases the entropy within your brain, dissipating heat as it goes. But more importantly, it allows you to become a local director of entropy's flow. When you decide to build a bookshelf from a pile of lumber, you are taking a disordered collection of raw materials and imposing a specific, functional order upon them. This is a local decrease in entropy, an act of creation. Yet, this act is powered by the energy your body burns from food, and the process of cutting and assembling the wood generates waste heat and sawdust, increasing the overall disorder in your environment by a greater amount. Your free will, in this sense, is your capacity to channel the inevitable increase of entropy in specific, purposeful ways. You are not a magical exception to physical law. You are a complex system that has evolved to harness these laws. Your brain acts as a kind of probability engine, weighing possible futures based on past experiences, and then selecting a course of action that will create a particular outcome. This decision-making process is a form of information processing that is thermodynamically irreversible. Once you make a choice, you cannot unmake it without incurring a further entropy cost. The path you did not take vanishes into the realm of unrealized possibilities, while the path you chose becomes part of the concrete, irreversible past. So your sense of agency may be the subjective experience of being a sophisticated node in the cosmic network, a point where the universe's statistical tendencies are calculated and leveraged to create local pockets of meaning and order. Free will is not about breaking the laws of physics. It is about using them to write a tiny but significant part of the universe's ongoing story. This computational view transforms the cosmos from a mere collection of objects into a dynamic process of information transformation. If the universe is a computer, then its fundamental components are not just particles of matter, but bits of information. Every electron's spin, every photon's polarization could be seen as a binary state, a 1 or a 0. The laws of physics, in this analogy, are not just descriptive equations. They are the operating system, the unbreakable code that dictates how these bits can interact, combine, and evolve over time. The Big Bang, then, was not just an explosion of energy, but the moment the cosmic computer was powered on, initializing the first simple state from which all computation would follow. The entire history of the universe, from the formation of the first hydrogen atoms to the rise of conscious life, is the result of this immense, ongoing calculation running its course. Each interaction, every collision of particles, every fusion reaction in a star is a logical operation, a step in a computation of unimaginable scale. This perspective makes the arrow of time feel intuitive. A computation has a clear beginning, a sequence of steps, and a final output. You cannot run a complex program backwards and expect it to make sense. The increase in entropy is directly linked to the number of computational steps that have been executed. As the universe computes, it generates new information, new states, and in doing so, it inevitably moves from a low information starting point to a high information, high entropy future. Think of a simple computer program that starts with a single number. With each operation, it adds a new number, multiplies or divides. The list of numbers it produces grows longer and more complex. It cannot spontaneously return to its shorter, simpler past states without a reset command. The cosmic computation is the same, but on a scale that encompasses all of reality. This metaphor also helps explain the emergence of complexity from simplicity. Simple rules, iterated over and over again, can produce astonishingly complex and unpredictable results. Much like the simple rules of Conway's game of life can generate patterns that seem almost alive. The universe's operating system, with its handful of fundamental forces and constants, has computed its way into galaxies, planets, and life itself. The ultimate output of this 14 billion-year calculation remains unknown, but the process itself is the very substance of our reality. We are not just living in the universe, we are patterns emerging from its continuous, relentless processing of information. That relentless, irreversible flow is the very wellspring of all that we find beautiful. We often frame the second law as a narrative of loss, a slow fade to gray. But this is a profound misunderstanding of its creative power. Without the imperative to disperse, to mix, to evolve toward higher entropy, the cosmos would be a frozen, eternal snapshot. There would be no drama, no transformation, and no story. The grandeur of a sunset is born from sunlight scattering through a turbulent atmosphere, a direct consequence of energy seeking equilibrium. The intricate structure of a snowflake emerges as water freezes, releasing latent heat into the colder air, a local ordering paid for by an increase in surrounding disorder. Even the very fact that you can have a childhood memory distinct from your life today relies on the arrow of time that entropy provides. Impermanence is not a flaw in the universe's design. It is its central feature, the engine of novelty. A universe in perfect static equilibrium would have no seasons, no weather, no life and death cycles. It would be a museum with only one unchanging exhibit: the fleeting nature of a cherry blossom's bloom, the gradual erosion of a mountain by wind and rain, the life cycle of a star. These are not tragedies. They are the essential acts of a cosmic story that is still being written. The beauty we find in the world is so often tied to transience, to the poignant awareness that a moment is passing. This emotional resonance is a direct echo of the physical law that governs reality. We are not separate observers of this process, we are expressions of it. Our ability to create art, to feel love, to ponder our own existence, all of this is possible only because the universe is unfolding, moment by moment, along a one-way street from order to disorder. To appreciate this is to see the cosmos not as a machine running down, but as a magnificent, ongoing performance. Its beauty lies not in permanence, but in its glorious, inevitable change. The warmth leaving your hands on a cold day is a whisper of the same force that cools a dying star. You encounter entropy not as an equation in a textbook, but in the mundane rituals of daily existence. Watch the ice cube floating in your glass. It does not stay a perfect geometric solid. The organized crystal lattice of ice is constantly assaulted by the random motion of warmer water molecules. The ice surrenders its structure, melting into the liquid, and the drink becomes a uniform, cooler temperature. This is entropy in miniature, a tiny drama of order dissolving into disorder, played out countless times a day in kitchens around the world. Or consider a log crackling in a fireplace. That would represent stored sunlight, chemical energy locked away in complex molecules by a tree over decades. The fire is a rapid, violent liberation of that order. In moments, the structured log is transformed into ash, smoke, and heat, its concentrated energy dispersed into the room and up the chimney. The cozy warmth you feel is the sensation of entropy increasing, of energy spreading out from a source to fill the available space. Even the most personal of experiences, the aging of your own body, is a story written by the second law. From the moment of conception, your body is an incredible feat of organization, building intricate structures from simple nutrients, but maintaining that order is a constant losing battle. Our cells accumulate damage over time. Proteins misfold, DNA acquires errors, and the complex machinery gradually loses its precision. We fight this decay by consuming energy from food, using it to repair and rebuild, but we always export more disorder than we import order. The heat we radiate, the waste we produce, are the receipts for this transaction. Aging is not a mysterious curse. It is the slow and inevitable increase of entropy within a biological system. Look at your own home. That tidy desk you organized on Monday will, by Friday, likely be a landscape of scattered papers, coffee cups, and pens. Left to itself, any system tends toward disorder. It takes a continuous input of energy and effort to keep things in their place, to fight the natural pull toward a more probable, scrambled state. Seeing entropy in these everyday moments transforms it from a distant cosmic principle into an intimate companion. It is the reason your car engine needs fuel, why your house needs heating, and why you need to eat lunch. This universal law is not happening out there. It is happening right here in the steam from your tea and the wrinkles on your skin. This constant humming activity all around us is the local expression of the universe's grandest narrative, connecting the cooling of your coffee to the ultimate fate of the cosmos. This unbreakable chain of cause and effect, governed by probability, does not mean the future is already written. The very nature of entropy ensures the opposite. While the universe's overall direction is set, the specific path it takes is fundamentally unpredictable. The engine room of reality is not a deterministic clockwork, but a generator of genuine novelty. Consider the simple act of flipping a coin. The laws of physics govern the toss completely. The force of your thumb, the air resistance, the precise geometry of the coin, all these factors determine whether it will land on heads or tails. In theory, if you could measure every variable with infinite precision, you could predict the outcome with 100% accuracy. But in practice, this is impossible. The tiniest, unmeasurable gust of air, a microscopic imperfection on the coin's surface, a fluctuation in the gravitational field, any of these can tip the balance. The outcome is not random in a magical sense, but it is effectively unpredictable because we can never account for the countless tiny influences, the countless degrees of freedom that will affect the result. This is the heart of the matter. Entropy-increasing processes scatter information. When you mix milk into coffee, the information about where each tiny droplet of milk began is not lost from the universe, but it is dispersed across trillions of jostling molecules. To reverse the process, you would need to track every single one of them and reverse their paths, a task of such monumental complexity that it is physically impossible. This irreversible dispersal of information places a hard limit on prediction. We can predict the average behavior of a system with stunning accuracy. We know that the coffee and milk will mix evenly. We can calculate the pressure and temperature of a gas in a container because we understand the statistical behavior of its molecules. But we can never predict the exact path of a single, specific molecule as it caroms off its neighbors. It is this microscopic unpredictability, when amplified, that creates the open future of our everyday world. A weather system is a perfect example. We understand the physics of atmospheric circulation, of heat and moisture perfectly well. Our supercomputers run immensely complex models. Yet, beyond a week or so, weather forecasting becomes increasingly unreliable. Why? Because the atmosphere is a chaotic system where microscopic uncertainties, like the exact evaporation rate from a single patch of ocean, are magnified over time and space through countless interactions. A butterfly flapping its wings in Brazil might, through a long and invisible chain of cause and effect, influence a storm system in Texas. This is not a metaphor for magic, but for the mathematical reality of chaotic systems, where small initial differences lead to vastly different outcomes. The same principle applies to the rise and fall of economies, the spread of ideas, the course of a human life. We are all complex systems, shaped by a unique and unrepeatable sequence of chance encounters, random mutations, and unforeseen events, all playing out within the broad, irreversible current of increasing entropy. The universe is not rolling toward a predetermined end. It is exploring a near-infinite landscape of possibilities, and at every moment, chance and contingency guide its steps. The engine room does not just unwind a cosmic spring, it constantly creates new, unexpected patterns along the way. This single, irreversible current flows through every scale of existence, weaving a tapestry of cause and effect from the quantum foam to the cosmic web. The story of entropy is the universe's great unifying narrative, a thread connecting the birth of a star to the firing of a neuron. It reveals that the laws governing a cooling cup of coffee are the very same laws that orchestrate the life cycle of a galaxy. This is not a reductionist tale that diminishes the richness of reality. On the contrary, it provides a profound and elegant context for everything we are and everything we see. The intricate dance of chemistry, the emergence of biology, the vast architecture of cosmology, these are not separate disciplines. They are different chapters in the same epic, all driven by the universe's fundamental journey from a state of low probability to a state of high probability. Our own fleeting consciousness, our capacity for love and curiosity, becomes a poignant part of this grand scheme. We are not accidental tourists in a meaningless cosmos. We are transient manifestations of the universe's ongoing transformation, local eddies of order that briefly shine before returning our energy to the great flow. This perspective imbues our existence with a solemn beauty. Our struggles, our art, our science, all represent a conscious participation in the cosmic drama. We are the universe's way of becoming aware of its own story, of questioning its origins and contemplating its destiny, in recognizing entropy not as a force of mere decay, but as the engine of all change and complexity. We find a deeper resonance with the cosmos. Our brief moment in the sun is given weight and significance by the immense, irreversible timeline of which we are a part. Our journey inside the engine room of reality reveals that entropy is far more than a measure of disorder. It is the fundamental principle that gives time its arrow, drives cosmic evolution, and makes life and consciousness possible. While it points toward an ultimate equilibrium, it is also the very force that creates the rich tapestry of existence we see today. As we look up at the stars or simply watch a candle burn, we are witnessing the same universal law in action. Let this new perspective inspire a deeper curiosity about the workings of the cosmos. Share your thoughts on this profound force in the comments below, and subscribe for more journeys into the heart of space mysteries.